the CO2 concentration in the air dropped down directly to zero.
What's the promise of artificial intelligence scaling climate tech? Join Zihui Zhou as he shares his insights. From breakthroughs in chemistry alongside Nobel Prize-winning chemist Dr. Omar Yaghi to China's evolving role in CCUS, we explore real-world capacities and the true cost of innovation. Join us for Capturing Conversations with Climate Leaders, hosted by the Future of CCUS Summit.
Welcome to Capturing Conversations with Climate Leaders. I'm here joined by Zihui Zhou, and we're going to be talking about his first publication on COF 999. Welcome.
Thank you, it's my pleasure.
Awesome. So let's start off with China. So growing up in China, was there a watershed moment you can think of that led you to pursue an academic career focusing on climate change, or was it something that you stumbled upon while pursuing your PhD studies here at Berkeley?
Yeah, I would say after graduation, when I was applying for the grad school, I was interested in both organic chemistry and material chemistry. So I wanted to combine organic and material together during my grad research. So that's why I looked for all the groups working on covalent organic frameworks.
Okay.
And because Professor Omar Yaghi at UC Berkeley is actually the pioneer and the inventor of this class of material, like covalent organic frameworks, or what we call COFs. So that's why he was my first choice during the application.
Okay.
And after I joined this group, Omar just assigned me to CO2 subgroup, and he said, okay, you can work on CO2 now.
Okay.
And that's the moment I know CO2 is a trouble, and we need to remove CO2 from the air, and we have some climate problem on CO2 from that time.
So walk us through the journey from ideation to where we are now. When and why did you guys start this research project?
Yeah, so for covalent organic frameworks, the history needs to go back to 2005.
Okay.
And same in this lab, the Professor Omar Yaghi's lab, the previous researchers invented this material by combining organic building blocks together. And they found a way to use small molecules to make porous crystalline materials that has infinite or a lot surface area to have gas molecule inside the pore.
Okay.
And after years of development, in year 2019, our lab actually developed a very stable covalent organic frameworks.
Okay.
And my research is actually based on the stable covalent organic frameworks. Okay. And I added a lot of functionalities inside this framework. You can imagine the functionalities as a small magnet for CO2 molecules to selectively pick up CO2 molecule into the pore. And in that way, this pore is functionalized and designed for CO2 capture. So that's the moment or the journey we started to invent this material, make a stable material, and finally make a functionalized stable material.
So COFs versus MOFs. Can you tell us in layman terms what the differences are between those two frameworks?
Yeah, so for both MOFs and COFs, you can imagine you are composing all the Lego building blocks together to build a whole building in a molecular level.
Okay.
However, for COFs, the name is covalent organic frameworks, and everything, all the building blocks are organic compounds. Okay. And there are only carbon, nitrogen, oxygen, or some light atoms in the building blocks. And for MOFs, that's metal organic frameworks, so this framework contains metal. Okay. So the difference just between MOFs and COFs are just metal or not. Okay. So for MOFs, because they're composed with metal, so if you want to use the metal for certain application, you can definitely use MOFs. And for COFs, if you want the backbone to be lighter, you can use COFs because only light atoms are inside this material.
Okay, so I'm sure you've probably had many conversations with your colleagues and with Dr. Yaghi about being able to scale this technology, correct? So could COF 999 be implemented at scale? And if so, would it necessitate fans in the same way direct air capture works? Or is it something that could be passive with natural flow?
Yeah, so actually this is a good question. After we published this work, before we published this work, we were actually working on the scale of COF 99, and currently we are still working on that. Okay. And we already finished the gram scale of the material, and currently we are working with some companies Like Omar Yaghi has a company called Atoko. We are working with that company to scale up this material, maybe to kilogram scale or to ton scale, to finally deploy this material. And after this material is being scaled up, we can actually use this material in a already designed process for other materials. So we are just replacing the material inside the process instead of designing a new process. And for the fan or like active or passive fan question, this is also very good. Like we need to consider in the future. For example, if we have enough wind speed, we can definitely use the passive. We don't need to use the active fan. However, because the kinetics of our material is really fast, and we can finish the whole uptake in 1 hour. So I would say if we want to reach to the ultimate kinetics, the fan will be considered required to speed this reaction up.
Okay, awesome. I mean, while we were walking through this beautiful campus, we had talked about China and their decarbonization strategies. And you had mentioned that the government there is focusing primarily on point source capture. So I was curious, can this compound be used for anything beyond DAC, direct air capture, like point source, for example, or no?
Yeah, of course. Actually, in the paper, we also measure the performance of our material by using different concentration of CO2, including 4% and 15%. So which refers to the flue gas capture and the coal flue gas capture and the natural gas flue gas capture. And the COF99 actually performed very well and taking up more than 3 millimole per gram of CO2. And also this COF can be used in the flue gas under humid conditions. So everything is good.
Awesome. So also from what we understand, this was an international, multi-institutional effort here in Berkeley to Chicago, all the way to Germany, right?
Yes.
Can you tell us a little bit about who else worked on COF 999 and what their contributions were?
So for this work, we collaborated with 2 professors, one in Germany and one in Chicago. And Professor Joachim Stauwel in Germany actually worked on the computational part of our material.
Computational?
Yeah, the computational part. And basically when we measure everything, all the sorption structure, we want to know how CO2 is staying inside the pore. So after we have some experimental results, and we send the results to him and his team, and he did the computation and simulation and see how CO2 is being absorbed inside the pore. And also we have another collaborator from U Chicago, and Professor Laura is actually giving us a lot of suggestions on how to set up the computation.
So did you have a lot of early morning 3 a.m. calls with German Zoom or no?
Late night calls.
Late night calls. Very cool. So I'd love for you to expand on this idea of degradability, right, which is seen by many as a barrier to being able to scale, right, one of the many challenges. We know that you've tested about 100 cycles, right? One of your colleagues had mentioned that. But can you tell us a little bit about what the upper limits might be outside of those 100 cycles?
Yeah. So actually our material is very stable at small scale. And if you scale this up and you find if in the future, if we find a good way to scale it up and keep the performance, then the stability of the material, we don't need to consider that. The material should be also very stable at large scale. And for the cycling stability, 100 cycle, we didn't find any degradation. And right now, we are actually running the material for longer cycles and trying to run the material in a device. So more results will be published in the future.
Because I was wondering, does it stop at 101 cycles, right?
Definitely not.
Definitely not. Awesome. So, you know, I have to ask, considering this is the zeitgeist of our generation, artificial intelligence, right? Can you think of any role AI can play or does play right now in your work?
Yeah, definitely. So right now, previously when we are working on this material, we didn't use AI and we need to design a whole process by ourselves. But now we have the process ready and we can give everything to the high throughput instruments to help us do experiments and use the AI to help us to analyze all the data and design the next generation of this material. So in our publication, we report this kind of strategy and we are using AI and machine learning and everything to speed up the discovery of more materials belongs to this family.
So you might be able to work at breakneck speeds compared to what you guys were doing in 2005.
Yeah.
Awesome.
Yeah, so everything will be faster in the future.
That's awesome. So I hate to be a bit melodramatic here and paint a picture like a light bulb going off in the head of Thomas Edison, but can you think of an aha moment that you might have experienced at the lab, and how did that feel for you and the team?
Yeah, I would say the aha moment in the lab came from when we finally pushed the air into our material, and we designed the whole process. And finally, from the CO2 concentration analyzer, we found the CO2 concentration in the air dropped down directly to zero. Which means that all the CO2 from our gas flow was taken off by our material.
Okay.
And our material performs very well after a few cycles. And we extended the cycle for 100 cycles, and all the data looks good.
Okay, super cool. So when do you anticipate seeing these compounds used to capture the tons and tons of carbon we need to within a commercial capacity?
I would say, like, currently, as I said before, we are working on a TOCO, like Professor Yaghi's another company. And on this COF. And also we are working on other COFs that's cheaper and easier to be scaled up.
Okay.
So I would say we can see the COF being used in a device in maybe 1 or 2 years.
Okay.
And we can do a testing in a device now.
Okay.
Yeah.
So you mentioned the word cheaper. I'm sure if you were at a table with a bunch of VCs, they would have asked you, how much does it cost, right? Yeah. Can you sort of talk to us a little bit about the cost?
Yeah, so currently for our material COF99, and we synthesize everything in the lab, so definitely if you calculate the cost, everything will be expensive. However, if you scale this up, the cost can be lowered down because COF99 only composed like carbon, nitrogen, oxygen, and hydrogen atoms, and none of them are expensive.
Okay.
So everything will be cheaper after you scale it up.
So earlier on, you showed us a little bottle with that yellow powder, right? If you were to sort of throw a dart on the wall and give us a price as to how much that little bottle costs, what would you think? Or what would you theorize it be?
So in the future, I would say currently, if we calculate everything, and everything will be like $1 per gram at the lab level. Okay. And in the future, everything will definitely be cheaper.
Okay, awesome. So I know you're working on making some improvements to the materials through this iterative process you've been laying out for us, right? Can you give us a preview or a little sneak peek of what those might be?
Yeah, definitely. So I said, like, after we publish this paper, we are also introducing a new process. And actually, for our material, we are playing with the organic building blocks. Like the COF is composed by organic building blocks. So we are playing with the building block to make it longer or shorter, or change the shape of the organic building blocks to make different COFs. And the final goal, like, we are also aided by AI, we talked before, and we synthesize a bunch of materials and measure the kinetics and everything of this material. And finally, we need to find a material with higher CO2 uptake and fast kinetics and cheaper.
Okay.
Yeah.
For you personally, what are you most excited about with your career moving forward?
So I would say, as a grad student, my personally speaking, my excitement comes from I can finally graduate.
Yeah.
And I don't need to worry about
getting those late night calls on the weekends.
Yeah, that's right. And however, I'm most excited that my personal research finally can be used in the market. Yeah. Like we find something connecting from the chemistry lab to the chemical engineering lab and to the material science lab, and finally we see some hope using the material in the market and in the real world.
Okay.
Yeah.
Well, yeah, I'm assuming that that's probably one of the biggest challenges researchers face in academia is seeing their work actually enter the real world in a very useful capacity, right, to help move humanity forward. So would you say that's one of the biggest challenges facing you as a researcher?
So I would say, as a young researcher, and we are working, like every one of us is working on the carbon CCUS projects, carbon capture, utilization, and storage project. And actually, this project is not only a chemistry or engineering project. It's a combination of both chemistry and engineering, and in the future, also some devices like from the lab to the factory. So everything needs to combine together. And as a young researcher, I would say the challenges comes from we need to learn a lot from multidisciplines. And we need to know everything all the steps together, and finally we can design the whole process and break the boundary between the different disciplines. Yeah.
Fantastic. So as a young researcher, you talk about the challenges of blending all of these three disciplines, right, together and synthesize them. How does that affect your perception or vision for where carbon removal will be in, say, a decade from now?
I would say, like, currently I'm viewing the whole market or the whole projects by the view of chemistry. And after I published this paper, actually I had a lot of questions from the chemical engineering people.
Okay.
And lots of professors and students came to me and asked a lot of chemical engineering questions. And I found that, like, for all the projects, we need to think more. And in the future, we need to collaborate together. And in the future, I would believe we have a strong collaboration between us and material and chemical engineering labs and design the material and whole process in the 10 years. And finally, we need to work together to scale the carbon capture material up and finally deploy that in the real world.
So you must be a very popular guy on campus with all of these people coming up to you and asking these questions from different departments. So Zihui Zhou, thank you so much.
Thank you.
Thank you for joining us here today at Capturing Conversations with Climate Leaders. Thank you. See you next time.